Hi, my name is Olsen. I'm a second year PhD student here at the University of Bath, based within the Crestwell Group here in One South. And my PhD is focusing on the automated and sustainable manufacturing of important building blocks for API manufacturing. So essentially, when it comes to the building blocks that we need for drugs and other sorts of medicines, it's a very long synthesis pathway. And one of the key solutions to that is, of course, automated synthesis. And the one piece of equipment that is the most beneficial for that is flow chemistry. It can speed up or even reduce the impact of more sensitive reactions on the substrates, leading to a cleaner reaction and a higher yield. Photochemistry, it enables us to access some very high energy intermediates, which normally are inaccessible through traditional chemical pathways. And when it comes to photochemistry, especially specifically our research, the reaction profiles that take maybe an entire day in batch can take maybe about 20-30 minutes in flow, leading to a much swifter synthesis. So for our amino alkylation chemistry that started off with a paper that we put out in 2021, one of the key problems we had is this over-alkylation, where we had a substrate which transformed to our high energy radical. And unfortunately, by leaving it in, for example, the batch setup, you can have additions of the other reagent twice, which we don't want. By doing it in flow and minimizing how long it's irradiated under light, we selectively get the mono addition rather than the di addition. Utilizing photochemistry clearly worked that whenever I received my crude sample from the NMR, and when I analyzed it compared to the batch procedure, where I essentially had my product and byproduct side by side, equal height, compared to the flow process, where essentially the byproduct, which I did not want, was a tiny little nub, really clearly showed me that flow chemistry was the way to go. I'd say the hardest part about the project so far is anticipating when things could go wrong. So say, for example, precipitation of the material within flow is a drawback. However, with the setup that Olsen has, the coil can be easily repaired if the precipitation can't be removed with traditional dissolution. So far in this project, I've probably learned a lot more within this PhD than my previous experience with flow chemistry. Just having this hands-on experience day in, day out of utilizing flow chemistry, looking at the advantages and disadvantages it can bring to the manufacturing and synthesis pathways that I'm looking into. And essentially, you learn something new every day with flow chemistry, what you can do and what new reaction pathways are just possible. What I would say to new students, I'd say come right in. This is an actively developing area. More and more big pharmaceutical companies are getting involved in flow chemistry as it's opening up new sustainable, cleaner, and higher yielding pathways that they are interested in, and they need chemists who can do it. Would I recommend Bath? Definitely. You've got a lovely, quaint, quiet city that is just lovely to just take a walk about. The university is up on a hill, nice, at least surrounded by nature. I frequently get to spot deer outside my office window, which is quite nice. And the department is just filled with just the loveliest people who I have gone to for any advice that I've needed. I can just pop into any office, say hello, and hopefully not stay too long with a cup of tea before I need to go back to my own work. So right behind me is the photosynthesis reactor, which is our workhorse for all our scaled flow photochemistry needs. We have a wide range of coils that we have within the equipment, which is already under the blue light. So right here is our 5 mil coil, which, as you can see, very simple setup. The reagent solution flows through the bottom right here, goes through all the way around the coil, and then comes out the top ready for collection. So the great thing that I love the most about these coils is essentially it is, in the simplest form, tubing wrapped around a piece of metal. And that's brilliant because if you have precipitation where it's so stubborn you can't get it out with acid, and if you don't want to shove down piranha solution, what you can do is unwind it, wrap it around, and you're ready to go again. When it comes to the system, an additional benefit that I love is the modularity. This system, you can hook up with the standard flow chemistry setup. You can connect to any equipment that you need, whether it be commercial equipment like I have behind me, or the custom equipment that I'm currently setting up in a different lab. It can be plugged and played anywhere that you need. And when it comes to the automated nature of my project, what's brilliant is it is cooled down, even down to minus 20 degrees, using an oil chiller. What that means is I can set up my slots, let it run overnight, and I can come in tomorrow, collect and analyze with the highest amount of time efficiency. When it comes to our chemistry, low temperature is critical. These radicals that we're generating are highly reactive. Room temperature or above, where we traditionally do most of our chemistry firmly, that would generate side products, byproducts, things we just don't want. By enabling us to use low temperature reactions, the photosyn means that we can access our desired products down at the level that we need. When it comes to our chemistry, we need low temperatures, minus 20, even minus 40, depending on what oil you use in the chiller. Now, what this means is that around the coil, that would cause, icing effect. However, by using nitrogen, we can blow it off and irradiate it with 700 watts of power, and we're still getting that high throughput, low temperature synthesis that leads to high yields.